Hi, it's time for another math easy solution. To discuss further into calculus with parametric curves, and now look at part 2 of the arc length derivation video series I've been going over. In my part 1, I went over the formula for arc length of just a simple parametric curve, and now we'll look at it for basically more general parametric curves. So recall from part 1 that the length of a parametric curve C, we'll call this C right here, and this is the curve like that can be written as y equals f of x. So if we could write it as a function, in other words, we can have a one-to-one function like this, which is again the same as my earlier video on arc length, but now if it's in parametric form where we can write x equals f of t and y equals g of t, such as this, then we could transform this using the substitution rule for integrals, and basically when we go from a to b, we have at a the x value is when the t or the parameter is equal to alpha, and then when x equals to b, the t parameter is beta, like this. T is equal to beta, t is equal to alpha, etc. And what we want is this length L across from here to here, L, like that. And I showed in my earlier video that just by using substitution rule, we could switch from this original arc length formula, which is integral of from a to b of square root 1 plus dy over dx squared dx, into using parametric form from integral from alpha to beta of square root dx over dt squared plus dy over dt squared dt. Yeah, so make sure to watch my earlier videos on arc length and the part 1 on arc length parametric form to see how I did this using substitution rule. But now I'm going to show it in more general. So even if C, the curve, can't be expressed in the form of y equals capital F of x, or just a function of x, i.e. a one-to-one function, as I just explained, the above formula is still valid, but we obtain it by polygonal approximations, which was the same method that I used to show this formula, and that was in my earlier video, so check that out as well on arc length. Like that, put a better arrow. So to do that, well, we divide the parameter interval from alpha to beta into n subintervals of equal width delta t. So we're separating the t parameter into delta t equal ones. So from t0 to t1 to t2, etc., they're all equal distances apart. But now, so if we let t0, t1, t2 all the way to tn, if they are the endpoints of these subintervals, then xi at the ith one is equal to f of ti. And here I quickly just added here. So if the I interval or the I endpoint is just some random one in between here, so this is just in general ti, then xi equals to f of ti, because remember, x is just a function of t, we'll call that f of t, and y is equal to a function of t, we'll call that g of t. Then yi equals to g of ti, and these are the coordinates of the points pi, which again, those are the xi and yi, that lie on C, and the polygon with vertices p0, p1, all the way to pn are these approximates C, or this polygon approximated, and this will make more sense as I draw this out. Now to do that, well, let's just draw an x, y coordinate system. We have x, y like that, and let's say the curve looks something like this. So again, it doesn't need to follow the one-to-one formula, so we could even have it a spiral like that, etc. Yeah, so we just have a random curve like this. We'll call this curve C, and now let's say we start off at this coordinate at here. This is at p0, and this is at x0 all the way to, well, this is going to be y0, like that. Yeah, whoops, I don't know what happened there. Anyway, so that's at y0, and then let's say we go all the way to pn, where again the coordinates here are xn, yn, and is the same thing as writing, well, this is the same thing as writing x, instead of x, or we'll just write it as f of t. So we'll just move this over. Yeah, f, yeah, I don't know why my tablet's jumping like that, but anyways, so we have f of, this is the same thing as writing f of xn, n, and then the y coordinate is our g of this is not, this is tn, and this is g of tn, just my mistake there. So like that. So that's just what it means when each of these has its own t parameter value, and then it corresponds to different x and y values, which again correspond to different points on this. So if we start off at p0 and move to p1, let's say we move it across somewhere here. This is p1, and likewise we get to p2, and then we keep going on, and let's say we get up to a point here, and again the delta x's don't need to be the exact same. We could have one different values across different spectrums here. It could be different delta x's, just that the t values need to be separated by the same amount, and those ones you could graph those on your own on the x and y, on the x versus t graph, and or y versus t graph to see how they're all the same. So instead, let's say we have at this point here, we'll call this pi minus 1, and let's say the next step is going to be pi like that. And let's say again we have a point here and a point here, etc. So now what we have is, if we were to draw this polygon, I'll draw this in red, we basically connect all of these points in line segments and to create a polygon, or just straight line segments like that. So from p0 to p1 and keep going and going, etc., all the way across. Let's say this one is like that. This is not too accurate there, but this is just for illustration purposes. And then all the way across there. Yeah, so now what we have is, well, yeah, we have line segments that we could approximate because we can determine the length of each of these segments. So for a general line segment from pi minus 1 to pi, so we'll call this one right here, this line segment, and I'll draw this in blue, pi minus 1 pi, and I'll call this a distance by putting these absolute value signs because we want the always positive value of it. And we can determine this by, well, using the Pythagorean theorem. Draw a right angle triangle like that, where we know that this distance, well, we can determine this distance, or well, at this point here is when the the x coordinate is xi, all the way across here, which is now at this point, this is xi minus 1. So the difference across here, we'll call this delta xi, and likewise we have across here, we have, this is yi, and then this one all the way across here, this is yi minus 1. So we have this distance, I'll erase this little line, yeah, and I'll write here, now we have delta yi, so the difference from top and bottom. Yeah, so now from recall from the Pythagorean theorem, we could determine this length, and basically recall the Pythagorean theorem with a right angle triangle is just pi minus 1 for our case. Like this distance squared is equal to the vertical and horizontal squares of those. So this is going to be, well, delta xi squared plus delta yi squared, and here we could square root both sides just to get rid of this that square root on that side, so we get a value like this. But again, we do plus or minus, but since we're dealing with an absolute value as a distance, we don't want a negative distance, we just want a positive, then we just look at the positive side. And now basically, as in my earlier videos on arc length, we define the length L of the curve C to be the limit of the lengths of these approximating polygons as n approaches infinity. So this is just one line segment, but now we want to go infinite amount, and this is going to be, well, that's going to be our full length, which is L equals to the limit as n approaches infinity. So we have a just infinite number of line segments of the summation. So now we sum up each of these line segments. We go from I equals to 1. So when we have I equals to 1, for example, we'll have P1 to P0. This is 1 minus 1. So that's our first line segment. From Pi is 1 to this is Pi minus 1 at 0. So P1 to P0, etc. So then now we have this distance across like that. And then when we plug in this square root, we get, well, we could write this as limit as n approaches infinity of I equals 1 up to n, and then square root delta xi like this, put a bracket around, squared plus delta yi squared, like that. And now the next step is to, well, find values for these delta xi and delta yi, or values or formulas for those to replace it to get a Riemann sum, like I've done in my arc length videos. And to do that, what we could do is use the mean value theorem. Recall this, and I'll go over it in a bit again. When applied to x equals to f of t, or as a function of a function of the parameter t on the interval ti minus 1 to ti, and basically I'll show that it gives a number ti star in ti minus 1 and ti such that, and I'll show you what this all means. Basically, if we were to graph the original function from on an x and y curve, which we had, looks like something like this. Just to go over, I'm just going to draw that in a miniature one so that we could draw the x and t graph. So at this point here, we were looking at and draw this line segment. So this is at ti, this is at ti minus 1. So, and then also this goes up to, this is at xi, and this is at xi minus 1, like that. So what we end up having is, if you were to graph the corresponding x and t graph, so this is t, this is x now, where x equals to f of t, like that. This is a function of parameter t. As you can see here, as ti minus 1 approaches ti, that's increasing, so we would have, let's say we were going from this point ti minus 1 to ti there, and as you can see, what happens with the x overall increases, but it gets farther out here, then it comes back down. So in other words, we could start off somewhere like here. We're increasing the x value, because remember x is on the vertical axis now, and eventually comes back down, but not all the way down. It's still greater than xi minus 1, just to show you how it looks like. So it looks something like this. Draw a better curve. So this is what we have. And where this value across here, this is our xi, and then across here is our xi minus 1. And now the next step is, well, we apply the mean value theorem, like that. And mean value theorem again states it gives a number ti star such that the derivative or the slope is the same as the average slope. So if we get a point across there, we'll call this value ti star. Then the derivative, or the slope across here, would be the exact same as the average one, which is from here to here. And so then these are parallel slopes, like that. And then at this point here, this is our f prime of ti star, like that. So that's a derivative there. And this one here, this is just rise over run. That's just the average slope, like I've gone over before. Where the rise over run, well, that's just going to be the rise. I'll draw this in blue. This one is ti minus 1, but we already defined these as to all be the exact same. So we'll call this this one delta t. And again, this equals to delta ti. So this is all the same. Every single one is going to be the exact same. That's why we just write it like that. And then on the vertical side, we have it like this. The rise is going to be xi minus 1. That's just going to be delta xi. Yes, so what we have is, thus, by the MFT, or the mean value theorem, what we have is the derivatives are equal. So we have f prime of ti star, so that special value ti star, we need to have one that equals 2, and then the rise over run, which is delta xi over delta t. And now what this means is, well, if we just rearrange this and move this over to this side, what we end up having is a delta xi equals 2. Now we have f prime, and then ti star, and then we have a delta t, like that. And that's what we have. And now similarly, when applied to y equals g of t, the mean value theorem gives ti double star, so another ti value, in ti minus 1 to ti, such that, well, we could do basically the exact same thing, but instead of dealing with x, we could deal with y, and we could draw y on the horizontal side, whatever graph you want. It's basically going to be reinventing the wheel, so you could play around with it yourself. It's going to be the exact same, but instead of x, we'll switch the values to y. So what we have is, if we were to do the exact same thing using apply the mean value theorem, we have delta yi. So delta yi equals to, I'll write this y a bit better again, equals to g. So instead of so it's a function of g instead of f. So we'll have g prime of ti double star. So double star like that, and then now we have the delta t again. And this is what we have for delta yi, and we could plug those two inside here. And then from there we have this delta t, so we could have something that looks like a Riemann sum. Yes, so thus what we end up having is when we plug in these inside the square root there in the limit, so thus the limit L, the length L is equal to the limit as n approaches infinity of the summation I equals to 1 up to n. And then we have square root, and now we plug these values in. So we have, this is going to be the first one at delta x I, which is fi prime, and then this is ti star, and then we have a delta t squared, plus now on this side we have g prime ti double star delta t. And then it's all squared like that. And now what we could do is, well, we could factor out the this part right here, which is delta t. When you square it, then it's on both sides. So and then there's a square root overall. We could factor out the delta t. So in other words, we can take out the delta t squared, which is square root, and again this gets to our delta t on the outside. So we could do that. You could just visualize it, do it on your own. What we end up having is, well, L is equal to limit as n approaches infinity of the summation I equals 1 up to n, and then we have now f prime of ti star, and then we have squared plus, move this around like that, plus g prime of ti double star, and then on the outside we factor it out and remove it out of the square root, delta t like that. So there is our length that's written as a summation, and we have it like that. And I'll put the missing bracket there. So yeah, we could just factor out this delta t squared, delta t squared like that out, because there's a square root, cancels. They both have it in the same terms, just move it up. So we have something that looks like that. And now what's interesting is that the sum here, this resembles a Riemann sum for the function. So basically if we were having these ti's, if they were the same. So this resembles not exactly. Remember Riemann sums, I put a video link below on that. This resembles this function f of t, square root of f of t squared plus g of, this is a prime there, g prime of t squared like that. So it resembles like this, even though, but the only difference is ti star and ti double star don't necessarily be equal the same. But if we assume they're the same, then we can write it as an integral. But again, this is not exactly a Riemann sum, because in general ti star does not necessarily equal ti double star. So this is very important to note. Nevertheless, if f prime and g prime are continuous, the derivatives exist of them, it can be shown that the limit above is the same as if ti star and ti double star were equal. Namely, and I'll show that again, note, I may prove this in a later video, so stay tuned. So if we just assume they're both equal, so assume they are, then what we end up having is, well, we could write this Riemann sum as an integral, because that's just, again, by definition, what we end up getting is a L is equal to the integral from alpha to beta, from the left end point to the right end point in terms of t, and then square root, and now we have this f prime of t squared. So we're assuming it's the same one like that, which in fact you actually do get the exact same result even if you don't assume that they're the same. And I'll show that. I might show that in a later video. Then dt. So so this is f prime of t squared plus g prime of t squared, all square root, and then dt. Yeah, so this is our answer right here. This is the exact same as part 1, but just written differently. Yeah, so thus using Leibniz notation, what we could do is just write this in the same form as in part 1. So we have the following result, which is the same form as in part 1. And we have, here's the theorem overall, summary. If a curve C is described by the parametric equations x equals f of t, y equals g of t, where t is between alpha and beta, where f prime and g prime are continuous on alpha to beta, and C is traversed exactly once, so we don't have to go back and forth, as t increases from alpha to beta, then the length of C, the curve, is equal to the integral from alpha to beta of square root. And now we just write it in Leibniz notation. This is the same thing as here. This derivative is the same thing as writing dx over dt squared plus dy over dt squared, and then all square root, and then dt. Notice that, and I also want to state that, notice that this formula is consistent with the general formulas in my earlier video, which was dealing with, well, the arc length is just integral of, well, L is equal to integral of ds, where ds squared is equal to dx squared plus dy squared. Now, make sure to watch my earlier videos on arc length to see that, but we could even see it from here. And basically, if we were to plug in this, I would just multiply this out. We have L is equal to, for example, integral, I'll just ignore the interval from there. So we have this dx over dt, I'll square these both sides, and then plus a dy over dt squared, and then this is dt. We could just square root and then dt squared like that, just so that it's the exact same thing. So we could plug this inside, and notice all of these just cancel with all of this as well. And then what we end up with is, well, that just equals to integral of dx squared like that, dy squared. Where in this case, this could be interpreted as ds, over here ds squared like that. Yeah, ds squared. And I'll show you what that means again. And now to show basically of how this looks visually, we could write this or draw this out as x y curve, and let's say we had a curve like this, where from here to here the distance across here to here is, yeah, so let's say this distance is this is our delta x across delta x, but let's say if we were looking for infinitely small, this change would be, well, dx, which is again the same thing as writing it across here as dx. So infinitely small, if we're approaching it, I'll just put an arrow like that. That just approaches dx. But from here to here, this distance is not dy. That's delta y. That's the difference from the y from here to here. And now the distance from, or the displacement from here to here in the arc length is, we'll call this delta s. And the reason this is delta s and not ds, and this is delta y, not dy, is because those values are based upon this infinitely small dx. In other words, to determine that, we would draw a basically an instantaneous slope across here. So we would draw a line that's tangent to this point at this very point here, and then from there we could draw a triangle. So then this distance from here to here, or this full length like that, is our ds, and then this distance across would be our dy, because this is all dependent on the dx, and that's what we always have an integral. This one's dt, but if you were dealing with just y equals f of x formula, as I showed above, it's dx. Then these ones are all calculated based upon that. And as you can see here, we just have a right angle triangle where ds squared is equal to, well, dy squared plus our dx squared like that. So yeah, that's just it. And then and basically the full length is the integral of this small fraction of this ds, like that. So yeah, just as we would find the integral when we're dealing with x like this, we have a dx, now we just have a ds, which is the distance of the arc length of an instantaneously small or infinitely small arc length like that. Anyways, hopefully you learned from this. You can watch my earlier video on arc length, in which I go over this in more detail if you haven't caught up on this. It's quite interesting stuff. Anyways, that's all for today. Hopefully you learned from this very extensive proof video. And again, make sure to watch my earlier videos on arc length. It's quite fascinating stuff. And there's for basic arc length formula dx, just use substitution rule, we get to this. But if you use the polygon approximation method, we also get that exact same formula, which is quite cool. Anyways, all for today. If you learned, and like always, yeah, thanks for watching, and stay tuned for another math easy solution.